So shall we start? So okay, ladies and gentlemen, I think time is right. Almost 1 minute to begin of the talk. So I welcome everybody on behalf of the organizers. I'm very happy to have everybody here and also some other people on the other side of the internet. And I think I will just declare the meeting open.
Our first speaker is Anton, and he will talk about supergeometry and super-Teichmüller superspace.
Thank you very much for invitation. I just wanted to make sure you guys see my screen, right? My shared slides.
Working on it. Sorry, I don't know.
Okay.
1 second. Sorry. I don't know why this thing is not.
Anton, thanks for the flag.
Okay. What is going on here? Should be here. Yeah. Okay. Sorry, it's just coming up. Okay. Should be okay. All right.
All right. Now you guys see the slides? Yes?
Yes.
Okay.
Yes. You can start.
Okay. Okay. So thank you very much for invitation. And before everything, since I'm the first speaker at this wonderful conference, I'd like to say a couple of words about the current state of events in the world, because this is unavoidable. Independently where you live or work, I think there is no way you can remain neutral watching the incredible cruelty of fascist invasion and the unbelievable courage of Ukrainian people fighting it. I can only hope that the civilized world will take a bit of that courage and end this horrible massacre to save Ukrainian people who are fighting for our freedom and yours. All right, so let me switch
How about
to
Ukraine?
yes, Slava Ukraini. So let me switch to mathematics now, and so my talk is about hyperbolic supergeometry and super-Teichmüller spaces. And let me first fix certain things. How we're gonna talk about Teichmüller space and superising. So let me take a Riemann surface of genus G with S punctures, and I assume that the number of punctures is greater than 0 and the earlier characteristic is less than 0. Now for Teichmüller space, I will talk about it in a presentation theoretic manner. So I'll talk about Holmes from pi 1 of that Riemann surface to PSL2R and conjugate by PSL2R. So Holmes in here, they're taking to be injective. And I want to make sure that the representation of P1 in PSL2R is discrete, and the group elements corresponding to loops around the punctures are parabolic. And this is where we get in touch with hyperbolic geometry, because PSL2R acts on the upper half plane and Lobachevsky geometry, and this is where it comes in. So and what we're going to talk about, so this is all classic stuff. What we're going to talk about is generalization of that when we replace PSL2R by sorry?
We do not see the lowest line. I mean, I couldn't read the lowest line. Yeah. Can you go back?
We'll talk about that first.
So the last line
Yes,
is
the last line is a problem.
So I don't know why it happens. Because
No, it's nothing on your end.
No, you said the maximize the zoom.
so the last line is just saying that the group elements corresponding to loops around punctures are parabolic, that the trace is equal to 2. But I don't know why the last line is not.
Prime stands for that, right? Home prime stands for what? What we mean of prime?
Those three conditions.
Ah, they're all three.
Is it
Can you, yeah, can you
Sorry.
keep it up? Maybe?
Yeah, there you go. That's perfect.
Okay. Sorry about that.
all right? Is it visible now?
Yes.
Okay. So we're gonna replace PSL2R with supergroups OSP12 and OSP22. So just in case if you don't know, supergroups and so on, I will define everything. So in these cases, you're talking about n equal to 1 and n equal to 2 super-Teichmüller spaces. The n stands for the number, basically number of half of the fermionic generators in this case. And the primary goal and the consequences of that goal would be to the construction of the so-called planar coordinates on those super-Teichmüller spaces. So that was originally a problem which was announced on Manin's seminar in the 80s, but it was solved later. So if you're interested, you can go to those references. So it's our papers with Bob and Ivan Ip and Yi Huang later on Supermachine, I think. But here is just contents of my talk. So first, I will talk about hyperbolic supergeometry. It's going to be quite an easy task in the sense that it's almost like calculus, just extra stuff, extra super stuff. And then we're going to talk about coordinates on super-Teichmüller space. Then we're going to see the first application of that. I will talk about Supermachine identity generalizations. And if we will have time, I will talk about n equal to 2 super-Teichmüller theory and some open problems. All right. So let me start from something very elementary. So since we're going to talk about everything in differential geometric terms, so I will talk about supercalculus adopted to that, so super schemes or anything like that. So let me start from exterior algebra over probably with infinitely many generators over RC. So then we're going to talk, we can define super numbers in the standard way. And just to fix the notation, I'm sure everybody has seen it. So there is a body of a super number, the first term in the expansion, and of course there are even and odd super numbers depending where you are, lambda 0 or lambda 1. And note that odd numbers anti-commute. So based on that, you can define superspaces and supermanifolds. So you're going to look at tuples of these elements, even and odd, and together they form a superspace, NM superspace. So the corresponding even and odd coordinates, those are just variables. So there are special spaces which we're going to need, and this is where the body of a super number is going to be needed, because you can define partial ordering based on that. So we're going to need the super upper half plane, and here is explicitly the condition that the imaginary part of the even parameter is greater than 0, and positive superspace, which can serve for us as a chart for super-Teichmüller space, it's defined similarly. All right. So since we talked about superspaces, let's talk about supergroups. So you can define the pairing there. Here it is defined by J for 1, 2 superspaces, and therefore the corresponding matrix which preserve that pairing. Well, you can talk about it as OSP12 group element. So why it's called OSP? Because it's orthosymplectic. So in J you see orthogonal part and symplectic part, and that's why it's called orthosymplectic group. So and if you look at the super matrices over here, well, the convention is that the even numbers there, they are defined by Roman letters, and Greek letters serve for the odd variables. So an important remark, yes.
Actually, this SPO is the way how you wrote.
Well, yeah, I mean,
J corresponds to symplectic part, symplectic block, and then
yes, it's just a matter of convention. Yeah, but I mean, depending on how you, I know that there was a lot of kind of say
Because actually your matrices are not 1, 2, but 2, 1. 2, 1.
Yeah. But I switched, so it doesn't really matter. They're all isomorphic, so it's
Yeah, they're isomorphic, but to avoid confusion.
I'm confused.
yes. I know that I misplaced it
I was
here.
confused.
Yes.
So what does mean is ABCD, they are even?
Sorry.
ABCD are even? No,
I-
doesn't matter. The ABCD, they are even?
Yeah, A, B, C, D, and F are even. Yes, and alpha, beta, gamma, delta are odd. So, and there, you see that there is a notation for supertranspose, that there is extra minus signs in comparison to standard matrices. An important remark here is that the body of a supergroup is SL2R, not PSL2R. This kind of little difference will make a lot of difference in the following, in the super-Teichmüller because it can be related to spin structures. All right. So since I talked about supergroup, let's talk about superalgebra briefly, because it's one of my favorite objects in supermathematics, because it's kind of like square root of SL2 in a sense that there are, in addition to standard SL2 generators H and X plus minus, the standard Chevalier generators, there is also V plus and V minus, which are kind of like square roots of X plus and X minus. In a sense that commutator between them is actually anti-commutator. It's super cool. And the killing form, the generalization of the killing form here, gives us a super-Minkowski space. So when we talk about hyperbolic supergeometry, the same way as it is done for PSL2R, you're talking about actually a joint representation of the corresponding supergroup. So here it is. Here it is, this Minkowski space over here, R212. It's just a space of a joint representation for OSP12. And here is your killing form. It gives you the pairing on this space. And important surfaces in there, super surfaces, are super hyperboloid and super light cool. So we're going to approach this hyperbolic geometry from this 19th century perspective, in a sense that we can represent everything as surfaces in super Minkowski space. Now, why I'm talking about the super hyperboloid and super light cone? Because there is actually an equivalent projection from hyperboloid to super upper half.
I have a question.
Yes.
So this you say OSP12 acts on this R212. So R212 has 5 coordinates. So how does it work with your 3x3 matrices?
No. It's an adjoint representation of OSP12. So let me just go back here. So you see there is 5 generators here: H, X plus, X minus, and V plus, V minus, right? So that's 5-dimensional, I mean 3 2-dimensional space, right?
But that's the same with that's the same thing as before the Lie algebra.
Yes. So you can think about PSL2R and its action in 3-dimensional Minkowski space, right? Right, because
Yes.
it's SO21. So but there will be a big difference between those because they're going to be orbits in there. So that would be important. All right. All right. So I'm interested, by the way, I forgot to mention that, the super hyperboloid, it has 2 components. So I'm interested in the upper half. And this upper half of the hyperboloid, so it has equivalent projection on the super upper half plane. And those transformations on the super upper half plane, and an important thing there is absolute, which is R11, and I call it a boundary, but obviously you probably visualize it that the boundary is bigger, but this is just a part of it, and so this is kind of an important part of the story. But nevertheless, so there is an analog of absolute for super upper half plane, and we call it R11 for now. So it is preserved by these fractional linear transformations, and they are those OSP1-2 transformations which act in the Minkowski space. So in the factor by discrete subgroup of OSP1-2, they're called the same way as Riemann surfaces appear. These are called super-Riemann surfaces. And at the same time, there are more general fractional linear transformations. So you can talk about T1-2, and those lead to 1-1 supermanifolds, equivalently n equal to 2 super-Riemann surfaces. But this is again another part of the story. Now for super-Riemann surfaces, there is another characterization, and I expect that Professor Rabin will talk about it. That you can think about those as 1-1 supermanifold with odd distribution, which locally you can think about it as what is called superderivative, which is square root of standard d by dz. And there are generalizations, as I said, that which correspond to SL1-2 subgroup. The corresponding factors gives us 1-1 supermanifolds, which do not have that distribution there, but they have relations to n equal to 2 super-Teichmüller. That's later. All right. So let's return back to this hyperbolic geometry in 19th century terms. So OSP1-2 doesn't act transitively on this light cone. So light cone serves like a boundary for that hyperbolic. But and as I said, there is R11, sorry, there is R11, which we treat as absolute, as a boundary. So there is an explanation what it is. So it doesn't act transitively, but the orbits are labeled by odd variable up to a sign, and you can just pick a vector like that in that orbit. The orbit of this vector creates this L plus theta. So notice that theta here is up to a sign. So there is a transformation which creates a reflection of the determinant variable. And the zero orbit, so when theta is equal to 0, that's exactly the projection for R11 to that absolute. And this is an important orbit which we're going to need for super-Teichmüller theory. Nevertheless, let's continue with hyperbolic supergeometry. Let's talk about geodesics there. So there are special geodesics. These are the ones with endpoints on the absolute R11, but from the point of view of again this Minkowski space, the endpoints lie on the rays of this special light cone L0 plus. And there is OSP1-2 transformation which makes them pure bosonic. So they end just on R in that sense. But general geodesics, they are labeled by fermions up to a sign. So they can end up on 2 different orbits of OSP1-2. And in principle, you can write the formula for the geodesic. It's very simple. It's not that different for any hyperbolic. Yes.
Let me ask a question. So what actually the word become means? So they become pure bosonic. Well, what does it mean?
So you can, so in this R11, you can kill basically the fermionic variable. That's what I mean. So the endpoint, they have like say Z1, theta1, Z2, theta2. So you can actually eliminate those theta1 and theta2. That's what I mean.
Make them 0. Eliminate means make them 0.
Yes,
Or?
yes. To make them 0. Exactly. Yes. But you cannot do it for general geodesics. So they will be labeled by 2 vectors, as you can see here, 2 vectors E and F, which generate 2 light cone rays, and they represent the endpoints. All right. So let's talk about this is important part. Let's talk about triangles in the light cone. So geodesics is like 2 points in the light cone. Let's talk about triangles. So first, there is unique OSP1-2 invariant for 2 linearly independent vectors. This is just a pairing, and we will call this pairing lambda length for the future. Explain why. But for 3 points, of 3 points, let's take a positive triple. So we pick orientation according to their bosonic, the body part. They will be labeled by 3 even parameters, A, B, and T, and 4 fermionic ones. Again, up to a reflection, so up to a sign. Here, alpha, beta, and epsilon, they will correspond to the orbits in the light cone. Those fermions labeling the orbits, and theta is known as Manin invariant. So in the case which is of special importance for us, when the orbits are L0 plus for all these 3 points, you can see there is an explicit transformation how you can put them in a standard position, so that the Manin invariant theta, it's an invariant of 3 vectors. This is one of the important things because it can serve as a coordinate for the Teichmüller space. So let's keep that in mind. And let me introduce another important thing in hyperbolic supergeometry, is a horocycle. So in this super sense, there are 1 2-dimensional spaces determined by the vector. So I'll pick the vector in L0 plus. And what they do something which any physicist would appreciate. They do renormalization of geodesic length, because in hyperbolic geometry, so because of the metric on the hyperbolic plane, the geodesic, well, it has infinite length, right? So those horocycles, the way they're represented here, the way they're drawn here is in the model of Poincare disk. So you map super upper half plane to the disk, and here horocycles, again in the bosonic sense, of course, they are represented by circles, and they chop off the infinite parts of the geodesic, and you are left with something finite. And moreover, in this Minkowski space perspective, you can represent this length, the renormalized length, using just the pairing between 2 vectors which form horocycles. So it's a really beautiful construction. So delta here is the geodesic length, and lambda, this is what is lambda length. This is just a square root of the pairing of 2 vectors and the light cone. Okay. So now let's talk about, so we have all the ingredients for the planar coordinates in principle, so I can explain it just in the bosonic sense. But let's first talk about why do we need all that, and why do we need planar coordinates? Because you want to realize what is called mapping plus group, because what people are interested in is not the Teichmüller space itself per se, even though it's interesting, right? But it's factored by mapping plus group. A group of homotopy classes of orientation preserving homeomorphism, because this is a moduli space. This is the ultimate goal of many studies. And these coordinates, planar coordinates, they allow you to represent the action of mapping plus group in pure combinatorial terms. All right, so how planar coordinates actually work? It was done in 1980s. So this is a construction of coordinates associated to ideal triangulation of our Riemann surface. So you look at the triangulation where the vertices are the punctures, and you triangulate your surface. So here is the example with genus 2 and 1 puncture. And you assign a positive number, that lambda length we were talking about, for every edge. That construction provides coordinates for the decorated Teichmüller space. So this is a bundle. Again, S is a number of punctures, and these R plus parameters are nothing but you can associate them with those vectors which form horocycles. So those positive parameters which determine the length of those vectors in the light cone determining horocycles, those cutoff parameters, they form this bundle. And the mapping class group is realized in a very simple way using the Whitehead transformations, so flips, and the lambda lengths behave in a very nice way. Here is a Ptolemy relation. I've seen it in many instances. Just a circle and inscribed relateral. You're gonna see the transformation between the diagonals. So, and there is a simple way to get the coordinates on Teichmüller space itself to remove that bundle, that decoration, just to pass to what is called shared coordinates. So those are logs of AC and D. So, but those will be subject of linear constraints. So basically, the sum of those around every puncture, they're gonna have to be 0. And so you will sacrifice something important. So those ZEs, they're gonna satisfy certain linear constraints. All right. Okay. So let's move to n = 1 super-Teichmüller space. So again, there is no big secret here. So we're gonna replace PSL2R by OSP12, and well, everything will remain the same. What we have to just check that those homes from pi1 to OSP12, when you strip out all the fermionic variables, you obtain those homes you had in the bosonic case. So you just want to make sure that those are really Fuchsian groups, which sit in PSL2R. And we just define the trivial bundle. So far, it doesn't make much sense, but just define it like that. And one thing which I mentioned for the following, so unlike a Teichmüller space, the super-Teichmüller space, it will have many connected components, and they will be labeled by spin structures. So we're going to meet spin structures on the way, not just yet, but just keep it in mind. It will have many connected components corresponding to the spin structure. All right. So in order to make this work, let's return back to our hyperbolic geometry constructions. So let's put 3 points. We discussed the orbits of 3 points on the light cone in the standard position, right? So that you will have 3 invariants, A, B, and E, and an invariant theta, Manin invariant, which we discussed. And now let's add the 4th point. So the 4th point will create another triangle, of course, and they will be the second Manin invariant. But the point is that, well, you just did it mechanically, right? Your calculus 3 student could do that if he knew a little bit of super analysis. But important observation is that if you do it just blindly, if you turn this picture upside down, you're gonna have this transformation. So that is not kind of a unique way. So if you have all this data, basically on the hyperboloid, and you want to lift it up into Minkowski space, you're gonna have some kind of non-uniqueness, right? How to do that? So what you actually have to have is yes.
Could I stop your flow? Could you just remind us again what is minus invariant? And the second question is, I'm not quite sure if I understand what it means fixing the sign of an odd parameter. Two questions. Remind us what is Manin invariant, and the second, what you mean exactly by fixing the sign of theta.
So remember that 3 points in the light cone. You can talk about orbit of those 3 points, and remember that there are pairings between those. Those corresponds to A, B, and T, right? It's just pairing between vectors. And we also talked about this extra variable, which is Manin invariant. So let me just turn back to this slide. And you see that these are 3 points right here, right? So there are 3 invariants which are pairings, right? And there is extra variable theta in there. which you cannot remove, right? This is that belongs to that's a kind of a model, a parameter of the OSP12 orbit of the point. But the point is that it's defined up to a sign. So there is a transformation which reflects its sign. So it's again, it's a fermionic variable, but up to a sign. But now, if you add the fourth point right here, so you can fix well, theta and sigma, but you have to kind of talk about relative sign between them, right? So, well, you can reflect the signs of both theta and sigma, but you can do it simultaneously. So there is a relative sign in there. And if you turn this picture upside down, right? If you do the procedure the other way around, you're gonna have a different kind of relative sign between them, and that's a problem, right? So if you want to treat A, B, and T as coordinates, right, and theta and sigma as well, so then this creates a problem. So you have to have a kind of direction how to go. So from say theta to sigma, and then that kind of fixes this ambiguity, right? But once you do that, and that will be given by the spin structure later. But once you do that, you can just keep constructing those, keep adding those rectangles, keep adding those triangles to the construction. And what you do, you construct a lift. Let's say you have upper half plane with triangulation, with ideal triangulation, and with all these coordinates. So you lift all this data to the Minkowski space, and fixing the fundamental domain, all this data gives you the generators of pi1. So you fix fundamental domain like in here. So you identify the triangle which sits on the inside, the triangle which sits on the outside. That creates for you the generator of OSP12, and then you are done. You construct the representation of pi1 in OSP12. But again, we have to talk about this kind of direction from sigma to theta, how to define it. So, and that's what we're going to talk next. Yes. So, so let's describe this way. How do we orient triangles with respect to each other? So for that, we're going to need I mean, you can do it using triangulations, but it's better to use the dual object, which is called fed graph. So the fed graph or ribbon graph, well, it's a graph which you obtain. You just put a vertex inside the triangle and stretch the edges basically perpendicular transversely to the sides of the triangle. And as a result, you will obtain the graph. But what we need to take into account there is the cyclic orientation of the corresponding half edges for every vertex. So if you fix that, you can reconstruct from the fed graph the entire Riemann surface with punctures. And here I give two examples of how to do that for one puncture torus and for three punctured sphere. And as you can see, as graphs, they're the same, but as fed graphs, they produce different surfaces because they choose different cyclic orientation for the vertices. All right. So this is just a dual object. So you can talk about triangulation or you can talk about the fed graph. It's completely exchangeable description. So now let's talk about the spin structures. So obviously you have seen the definition of the spin structure manifold, but for us it's kind of irrelevant in the sense that we want to have a combinatorial description, again, using some orientations of how you pass from one triangle to another. So there are several ways of describing spin structures on a Riemann surface. So one is due to Dennis Johnson and also Mumford. It's using the quadratic forms on H1. There's a quadratic form with respect to intersection pairing. Another one, which is more explicitly relevant for us, it's through the lifts from PSL to R to SL to R. When your Riemann surface is defined, as a factor like the Fuchsian group. And there is a very simple relation from this description to the description above, the Johnson description. So you're going to just look at the trace of the corresponding element and look at its sign. Yes, there is a question? No? No. And there is another description which was very, very useful for us. It's the description of Chemazonia-Teichmüller. That was a combinatorial description of spin structures using Castellan orientation, dimer configurations. I'm not going to talk about it because I will present a simplification for our Fed graph description of the Riemann surface in a second. So all of this, by the way, all of these descriptions are very, very useful for us. We're going to use them. So here is a description of the spin structures. So this is, again, very, very simple. So you look at the Fed graph and just put orientations on it. So clearly you can take a graph and put orientations. And you look at the factor of these orientations with respect to reflections at vertices. So you're going to take, let's say, one vertex and reflect all the arrows at that vertex. So that creates, taking all such reflections, that creates an equivalence relation. And it turns out that those classes, they're in one-to-one correspondence with the spin structures. Moreover, with respect to those flip transformations, remember for triangles, we had the transformation which just exchange the diagonal, right? You take two triangles as a quadrilateral and exchange the diagonal. For Fed graphs, it looks like this. And here, epsilon 1, epsilon 2, epsilon 4, these are just orientations. And this is how you can unifyingly define the transformation corresponding to the flip. So you're just going to change the epsilon 3 sign there. So, yes?
And is it possible to say it combinatorially in terms of triangulation directly? So
yes. So in principle, you can. It's just more kind of transparent on the level of Fed graphs, but you can translate it just because the orientations on the edges of the Fed graph, you can translate them into orientations on the edges of triangulation. So, and if you're interested, we use it. We use this version in the Super McShane paper, and this is also a possibility. So, but it's just on the level of Fed graphs. It's very, very transparent.
So I'm going to clarify. So that means you have your triangulated surface, which is obviously oriented as a surface. But besides that, on each edge of your triangulation, you fix orientation.
Yes.
Edge.
Yes.
And
there are equivalences. So you have to factor by equivalences, which correspond to the reflection of the.
And this is the extra piece of data that you need to fix those things that you call Manin invariance. So
yeah, exactly, the relative signs between them. So if you want to
signs, who is sigma and who is theta, right?
Exactly, because you have to point the arrow. Because as I explained to you, if you flip the kind of picture around, you're gonna have extra minus sign that creates an ambiguity. But once you add this piece of data, once you add this kind of arrows which point from one triangle to another, that problem pulls away.
So you need to know when you move along the edges of your triangulation, you need to know who is at the left and who is at the right. So that's a choice that you need, right?
No, not on the left or on the right. It's somehow
Well,
I mean-
because you have general, you have orientation of the whole thing and the orientation of the edge. And this gives you something like co-orientation of the edge, direction with the left and
Yes,
right.
yes, 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 yeah, because
Co-orientation.
you're on the even surface, so you have canonical orientation.
Yes,
in
you
a
have
way,
canonical
yes.
orientation, rotation
Yeah.
of the edge. That means
Yes.
orientation in the normal direction. That
Yes.
means choice of left and right.
Yes, 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 absolutely, yes. Yes. All right, and by the way, these formulas are in general, in the sense that in low genus case, you will have some, this formula has some changes. So for example, in Supergeometry paper, there is one puncture torus, so there's going to be some change in the flip. All right. All right, so let me just describe these coordinates just step by step. So you're going to see the whole construction. So let's fix the surface. Let's take a trivial fed graph spine. So the fed graph associated to surface. Let's pick orientation on the edges and the corresponding class of those orientations. And here are the coordinates on the corresponding component of super-Teichmüller space. So there is a lambda length for every edge, and there is an odd coordinate, which we will call mu invariant for Manin, for every vertex of the fed graph or for every triangle. And that one has to be taken up to overall change of sign. So we can change all the signs at once. And alternating the sign in one of those harmonic variables, one of the mu invariants, they correspond to the reflection on the corresponding spin graph. So altogether, this gives us a chart of this kind. So there is 6g minus 6 plus 3s even variables and 4g minus 4 plus 2s of odd variables. And as you, some of you know, that fermionic part corresponds to the dimension of 3 halves holomorphic differentials, and that's not surprising. Kind of part of the deal. So, another description of Teichmüller space and supermodeling space. Well, anyway, this is a chart. And the corresponding flip transformation in here, well, it is given by the following formulas. So you see that there are some square roots available here. So there is some extra data, but in principle they could be kind of effectively removed. And I think one of the talks after mine is going to deal with that. So there is obviously a cluster algebra continuation. So I expect John can talk in housework together with Musiker, they had some progress in that direction. But at the same time, you see that those square roots, they appear near the kind of important part, near the fermionic variable. So if you do this flip transformation, so you won't have like square roots of square roots of square roots. That won't happen here. Note that in this picture, again, it has to be accompanied with the transformation of the fed graph, the transformation of the real-oriented fed graph. So this sigma and theta here, they're taken with the corresponding orientations. Right? All right, so these coordinates, they behave naturally with respect to mapping class group action as promised. Now, an important feature over here is that there is actually a two-form, the analog of Weil-Peterson two-form, which is invariant under Ptolemy transformations, therefore mapping class group. So here you sum up over all the triangles, so along A, B, and C, and you have extra part minus d theta square. This is what actually fermionic variables add up. So this is kind of, in a way, a miracle, because you see how complicated are those flip transformations, and there's extra square roots and so on. And this is just how that form is modified with respect to the Bosonic version, right? So this is just extra term minus theta squared. This is a kind of miraculous thing. Probably not, just You have to generalize the construction to see that it's not a miracle. But anyway, sorry. So, and again, as in the bosonic case, you can take shear coordinates for every edge, but they will be again subject to linear relation. And by the way, this is not all the decoration to be removed. So there is something extra you can chop out in the fermionic direction, which we're going to discuss a little later. Actually here, yeah, sorry, I forgot. So there is extra part which you can chop. So you can think about not R plus S decoration, but R plus S NR decoration. So what is NR here? So this is a number of Ramon punctures. So the corresponding small contour around the puncture, right? So that curves corresponding group element corresponding to that. It has trace greater than 0, so the quadratic form is equal to 1. So if you make a constraint that the monodromy group element becomes true parabolic, so it's conjugated to parabolic element of SL2R subgroup. So you remove all the kind of fermionic part, and you just end up with parabolic element of SL2R, just upper triangular matrix with 1 ones on the diagonal and upper triangular part, lower triangular. So that constraint can be formulated in terms of shear coordinates. You can write certain linear relation, and that will remove the decoration. And this space which you obtain after you remove it, this is what is physically relevant. This is what is relevant for physical moduli space. All right. So how much time I have? So let's talk about some applications. So one of the applications of this construction is the so-called Mach-Chain identity. So for one puncture torus, the Mach-Chain identity, it's this again miraculous formula. Well, we represent 1/2 as a sum over this 1 over 1 plus c to the L gamma, where L gamma is the length of simple geodesic gamma. This is a sum over all simple geodesics. And there are several ways of proving it. One is most algebraic, I guess. It's due to Bowditch, and it uses the so-called Markov triples. So that uses the fact that Teichmüller space for one puncture torus, so it can be identified to Poincare disk, and the corresponding templation of the Müller space, it's given by the Farad isolation, so equal rational points on the corresponding disk, right? So if you represent it as upper half plane, on the absolute you pick rational points, and that creates this triangulation picture. This is in black in there. Now you can construct a dual, what is called dual curve complex. It's not a cell complex because there is infinite amount of cells joining each other, but it's kind of a dual complex where the corresponding faces can be identified with geodesics, right? And these relations, these Markov tables, which we are discussing here, these are just relations between traces of the corresponding group elements, which preserve these geodesics. Well, manipulating with that and certain other relations, you can algebraically prove this Mach-Chain identity. So in super case, this Markov triple can be generalized in the following way. So here W's, these are these fermionic additions, and H here is extra parameter, which is you can rescale it. It is what is called super semi-perimeter. This is part of the length of the horocycle around the puncture. And using this this Markov triple and Ptolemy relation for the cusp torus, so you can prove the analog of the Maxine identity. So let me just explain how it works. So here there are several ways of treating it. So one way of looking at the Bowditch relation is, as I said, using the traces of the corresponding group elements which preserve geodesics. But you can also think about them in terms of lambda lengths. This is what we do here. And the relation, you can see it on the last line, the relation between the traces, in this case, super traces of the corresponding group elements, the length of geodesics, and the corresponding lambda lengths of the ideal arc, which doesn't intersect the corresponding geodesic. It is given by that formula below. So this is a bunch of algebraic formulas which actually later lead to the formula, which is pretty much analytic in its nature. And combining all that together, this is the analog of Maxine relation for the super case for one puncture torus. So this is an important generalization. And the idea of it, you cannot really break it in pieces in here, right? So you cannot. So these W elements, which are the product of Manin invariants in there, they cannot be kind of separated. So I mean, immediate thing that you can break this formula in two, you cannot, because the lengths here, they depend on the fermionic parameters as well, so you cannot really break it in pieces, right? So this formula is kind of, from what I know, this is the first kind of application of kind of algebra and analysis, because you have to make a lot of estimates in there for supergeometry. So this is a very interesting combination of kind of analysis and algebra at the same time, applied to super case. This is, again, the first instance I have seen something like that. But of course, Maxine identities, they can be generalized, and there is a very interesting paper by Witten and Stanford regarding that and generalizing Maxine relations with respect to Mirzakhani's work. And this is an important, it creates a guideline for mathematicians to prove those. All right. So another direction which I wanted to point out, and this is what we did with Albert Schwartz, and somehow still didn't put this paper online, hopefully maybe this year. It's related to kind of a dual construction to Penner's work. It's using Jenkins-Strebel differentials. These are differentials with certain polar structure related to the Fed graphs. And that gives a very nice kind of dual construction to Penner's decomposition of Teichmüller space with respect to its cellular decomposition. So this is convex hull construction. And there you can, in our work with Schwartz, we constructed the deformations of one supermanifolds, and later n equal to 1 super-Riemann surfaces, n equal to 2 super-Riemann surfaces. We construct deformations using corresponding Cherenkov cycles associated to the Fed graphs. So this is a kind of a separate topic, but which is it's a kind of dual thing to Penner construction, more analytic. And by the way, there is so far we can construct an explicit analog of Strebel differential in the super key. So there is a deformation which is related to that, but the super analog of Strebel differential, we can do it. So it's an interesting question. All right, so let me, I think I still have 5 minutes. So let me discuss n equal to 2 super-Teichmüller theory, just briefly. So in this case, you are generalizing from OSP12 to OSP22, which is, well, on the level of Lie algebra, it is isomorphic to SL12. So it's better to work with 3x3 matrices than always when 4 by 4, you just have to add the extra automorphism to that, just to have this OSP2 structure. So in this case, well, SSL12, so it's a natural generalization of what we had for OSP12, so nothing is preserved in there except for the determinant, and everything remains the same except that underlying body of your group is not SL2R anymore, it's GL plus 2R. So there is extra parameter corresponding to the determinant. So cutting things short, in this case, an important extra object which you have to introduce is graph connection. So graph connections were studied in particular by Fogg and Rossley. So if you look at the connections on your Riemann surfaces with zero curvature, so you can discretize them in the sense that you can associate the monodromy to the flat graph edge, and this way you can think about the corresponding connection. In this case, it's just abelian connection. You can associate just a group element, the group element corresponding to that monodromy to the edge, to the oriented edge, of course. For the opposite orientation, you will have inverse element, and there are gauge transformations corresponding to the vertices. So this is what is called graph connection, and that extra piece of data is needed to describe this extra determinant part. So to give you explicit formulas in here, let's just look at the pictures. It's easier. So in comparison to what we had in n=1 case, so now there is 2 parameters per each triangle, 2 extra fermionic parameters per triangle, and there is this graph connection, just R plus graph connection. So to every edge you associate an element of R plus, and to opposite orientation it's inverse element. So this is those pieces of data, and you can construct the flip transformations. As you can see, that graph connections become deeply involved in all those, so they kind of mixes all variables together, these H parameters, and that kind of gives you the complicated structure of n=2 theory. Well, in some way, n=2 case, it's kind of physically more relevant in a sense, and more interesting, because those Riemann surfaces which you obtain, this n=2 super Riemann surfaces, they one-to-one correspondence with 1-1 supermanifolds. For 1-1 supermanifolds, you actually have as a body, you have the Riemann surface and the bundle over the line bundle over. So those 1-1 supermanifolds which you obtain using this uniformization picture are those of kind of middle degree, when your line bundle is degree 1 minus g, the square root of the all right. So let me just talk about some open problems in the remaining 1 minute. So first of all, there are cluster superalgebras, and I expect the next speaker to talk about it, to talk about the progress in there. So another problem, again, I put here them randomly, not in the order of importance, but just problems to think about. There is Weil-Petersen form. There should be a Weil-Petersen form in n=2 case. We didn't write it, but it would be a very interesting combination of planar-like Weil-Petersen form, which you sum up over all triangles, and the Fogg-Rossley 2 form, which should be weirdly combined into one. So it's just an interesting combinatorial thing to construct this form for n=2 case. Now, then there is quantization of super-Teichmüller spaces. There was a paper by Kirchner and collaborators on that, but I think there is a lot to do there. now there is analogs of Weil-Peterson volumes in super case. So it's, you can look at Mirzahani work and others in that direction. And those machine identities, they play an important role there. There is a relation to stable theory, which I talked about a little bit. And let me also mention the abelianization, which became very, very popular recently in the sense of Gayota-Murnetsky, the spectral network. And from a abelianization point of view, and that's why I was talking about n equal to 2 case, it's kind of more important. So for abelianization, you actually, from what I see, you will have to look at n equal to 2 case, and it will be quasi-abelianization. So you will look at GL11 with connections and graph connections. And by the way, I have a upcoming paper with undergraduate students on combinatorial description of GL11 kind of Teichmüller space in a way, which is also kind of very interesting combinatorial thing. So let me maybe stop here and I'll take questions. Thank you very much.